I'm going to go back to this speech class with 26 students labeled A through Z, each letter of the alphabet, 26 letters. Today we're going to give away 3 different preloaded Visa cards. One's worth $500, the other's $250, one's worth $100. That'd be awesome. Now, here's the deal. How many ways, if they have to be different people, how many ways can students receive the $500, the $250, and the $100? Well, any one of 26 people could get the $500 card. That leaves 25 left to get the $250 card and 24 left after that. And this is that permutation formula where, since it's decreasing by 1, we could take 26 factorial, which is 26, 25, 24 times 23 factorial, and if we divided it by 23 factorial, so we did 26 factorial on the calculator divided by 23 factorial, we'd be left with this number right here. And that is the permutation formula of n choose r things. In this case, permutation of 26 choose 3. Now, here, let's suppose the 3 people that were selected are person A, B, and C. But because the order matters, each one of these different arrangements or permutations are unique. In this situation, A gets the $500 card and C gets the $100 card. In this situation, C gets the $500 and A gets the $100. So each one of these permutations is distinctly different because the order in which the people were selected is important. It matters. That's a permutation. But what if we change this problem up just a little bit, and we're going to give 3 different people a card, so they have to be different people, but the preloaded amount, they're all $100 cards. So they're all the same. Well, now, do you agree it doesn't matter what order we selected them in, because they're all going to get this exact same prize, a $100 gift card. So now the order in which we select people is not important. And these 6 different permutations all become one combination called the combination of person A, B, C. Because it doesn't matter what order they're in. It just matters that, hey, if these are the 3 people selected, they're each going to get a $100 Visa card. So what happens is we go back over here, and when we calculated the permutation, we had 26 times 25 times 24. That's how many arrangements could get the $500, $250, and the $100. Among those many arrangements are these 6. But if the order is not important, if it doesn't matter, and they're all getting the same Visa card of $100, then every group of 6 permutations containing the same 3 people is just a repeat of the one combination of these 3 people being selected. So these people could be arranged 6 ways. 3 people to choose from to put in the first slot, 2 in the second, and 1 in the third. So that tells us that if we divide the number of permutations by the number of ways that we could arrange any of those 3 different people that were selected, this will eliminate the order being important and just give us the answer of how many combinations there are, how many groups of 3 people regardless of the order that they were selected in. So this then is how we find a combination. We take away the order being important by dividing by the number of ways that the people could be arranged. So here we go. Let's make sense out of this then. The permutation formula looks like this. It's the permutation of 26 choose 3 is equal to 26 factorial divided by 23 factorial. Remember, that cancels 23 through 1. But now that's the permutation formula. The combination formula of 26 things choose 3 starts out by figuring out how many permutations we have. That's this right here. This is equivalent to that. But now we have to divide by the order being important. And so we divide by the 3 factorial, which is the number of ways the 3 people selected can be arranged, so that these 6 permutations collapse into one combination. So the only difference between a permutation formula and the combination formula is that we divide by how many ways you can arrange the things that were selected. That eliminates the order being important from the process. So the basic formula then for permutation, it's a permutation of n choose r things is n factorial over n minus r factorial. But the combination formula of n choose r things starts out the permutation way, but it also divides out the number of ways that you can arrange the r things that are selected. That's r factorial. So that will give you the combination formula. This is the guy we need going forward in statistics. We're going to get to binomial probabilities. We just want to know how many ways can you end up with 3 successes out of 5. We're going to count the number of ways that can happen. The order is not going to be important. That's the formula that shows up at the beginning of the binomial probability formula. So it's combinations that we're more concerned with going forward. To give you a quick indication of where we see the combination formula and the binomial probability formula, this is going to be the binomial probability formula. Hey, there's p and 1 minus p, the probability of success and a failure, so it'll make sense as we get into it. But you got to multiply those probabilities by the number of ways of getting a certain number of successes out of your sample. But that thing right there is just another way to show combinations. So it's equivalent to this down here. So remember how we did a combination of 26 choose 3? If we use that in here, then this is how it would look. That just means a combination of 26 choose 3, and you go to this guy right here, or you bust it out in formula form right there. So we're just going to need to show work in the binomial probability formula that when we see that, that's a combination of n choose k things. So we'd want to show this work if we were doing a free response problem.